The webinar will start in a few moments. Good afternoon, everyone. I would like to welcome you to our third part of the Revealed series webinars. The first two parts, we went over the ROI calculations and what are some of the results of our customers have seen from converting to ceramic casting media. You can find all of these on our website if you have missed any of them. Also, you'll be able to catch this one afterwards as it is recorded, and we'll have it up on the website within the next day or so. The title of our presentation today is Revealed Part 3, How Does Ceramic Media Compare to Silica Sand? Discussion with FEF Universities on Ceramic Casting Media. In this webinar, we will have university experts talk about some of the testing they offer to compare these different materials. Hello, my name is Ray Jansen, and I am the Industrial Sales Manager at CARBO. Please submit any questions through the webinar portal, and we will answer them at the end of the presentation, or at least a couple of them. Now, I would like to move on to introducing our guest speakers, first of which is Dr. Sam Ranrattan. He is part of the Foundry Educational Foundation, better known as FEF, and a key professor at Western Michigan University. He describes himself as a good guy looking to make good casting, and you can see this by how involved he has been in the Foundry community. I'll leave up this for a second if you want to read it, and then we'll move on to Jerry Teal is our second speaker. Jerry is also a member of the FEF, and he is the director of the Metal Casting and Additive Manufacturing Center at the University of Northern Iowa. He has also been very involved in the AFS and has been the chairman of the Molding and Materials Division, the Additive Manufacturing Division, and Cast Metals Institute. At this time, I'm going to turn this over to Dr. Sam and let him begin his presentation.
Okay, good afternoon from rainy Kalamazoo, Michigan, where sentiments go out that we wish everybody is well out there. On this webinar, my topic is alternative granular media as chemically bonded foundry sands qualification strategies. What that really is, we're looking at a performance predictor when we put a chemical binder on these foundry sands. However, my particular focus on ceramic sands started with CARBO ceramics close to 30 years ago, when it was when we were involved with this material in the industry as what was described as a propellant. But in that time, there was no discussion about silicosis. It wasn't a commonplace issue, PEL and all of the issues around the silica law. We were trying to use the ceramic media to make a better casting. In recent times, the AFS supported some research right here at WMU, and we employed similar types of strategies. How do we make better castings with the use of superior granular media? Today, the major focus is to compare System A, a sintered aluminum oxide, to System G, which is the control silica sand based system. On this slide, I'm showing you the 7 media that was selected by the AFS, and these were selected solely on the availability of the media at that time for AFS to study and look at. What you could see across these materials are the properties that we documented for the sake of this study. By no means are they all the engineered properties. Certainly we can select mechanical, thermal, physical, chemical, and in certain cases, electrical properties as we try to passivate certain sand systems as we pour them. But the fact is, for all natural or synthetic alternative medias, we could find useful properties. But certainly, as we look at as we look at the ceramic sands, one of the things that we need to certainly understand is the as-cast surface quality. Today, when we talk about surfaces and castings, we're talking about machine surface finish or the surface finish from a sand casting. That does not really help us deal with the marginal benefits that we get from ceramic sand media. But way back when we began this research, we had a 2D means of comparing the silica sand in sphericity and roundness. So you could see the shape factors. But if we added the AFS GFN so that we could get the size comparison, we could get a 3D view. Today, we have more sophisticated tools, such as non-contact measurements of surface finish. And I'll be showing you that later. What we're still using in the industry is a C9 cast microfinish comparator. This is the standard at AFS. And this does not allow us to get to digital production. And I'll try and point out why that is important. But certainly, if I get back to the green shape for a moment, the idea here is just to let you know that the more angular, the more compounded that shape, the more chances that it could break down. And certainly this issue of durability is important for alternative media because these alternative media are significantly more expensive than silica sand. But there is no relationship. Certainly, if we look at the grain fineness number as defined by AFS and the as-cast chemically bonded sand quality that we get, when we put a binder on that sand and it meets molten metal at the mold metal interface, that's where the magic happens. And that particular magic is due to thermomechanical, thermochemical, thermophysical properties. And I want to talk to you certainly about how do we get to qualify that? How do we performance predict what will happen there? But before I go there, I have to talk a little bit more about the durability of these sands. And what we do at Western Michigan University, because these are some non-standard approaches that have been placed at the forefront of AFS to consider, we look at a distribution of sand and we try to break it down according to the typical ways the foundry industry has that depreciation of that sand. And the two major mechanisms is really impact and abrasive wear. Those happen time and time again through molding, melting, and filling, certainly at ambient, through elevated temperature. But should we look at a distribution, what happens is that we have the particle size change, especially the larger particles, and we have the distribution change at the same time. And because of that, it's hard to compare. So what I'm trying to suggest is that the smaller particles are protected. If we look at the distribution after impact and after abrasive wear, like I am depicting on this slide, such as a ball mill test or abrasion, the smaller particles appears as there was no effect. But the point is, should a granular media be superior in both toughness and wear resistance, we are suggesting that it will be durable for mixing and blending, and the mechanical reclamation process used in foundry processing for these ceramic alternative media. The durability at elevated temperature is also being investigated in our work. And what we're suggesting here is something that is true for all the media that we would see. On the left, I'm showing just two of the sands that we studied. On the left is the as received compounds that we see in the material. And then after elevated temperature treatment, that elevated temperature treatment in the AFS study was 1450 degrees C, which is typically the iron processing temperature. And what you see, some of these hard compounds, mullite, corundum, salamontite, these are in the top 12 hardest materials known to man. And they change in proportions when they are treated at elevated temperature. That also affects what we call the pulverization index. This is a measure then of durability as we look at ambient to elevated temperature treatment, from abrasion to ball mill impact. And to keep things simple in our study, we weighted things rather equally. But what we are seeing, certainly as we look at system A, the system that we are dealing with in terms of a ceramic media, it is superior. The higher number of the pulverization indexes is more resistant to that breakdown. And then system G is a silica sand. The other thing that we'd like you to glean from this slide is the mechanism of breakdown does not always act the same. Certainly, we see the ceramic media as superior in terms of its abrasion and wear resistance, especially at elevated temperature. But if we could reduce the amount of impact in treating sand systems in the foundry, mold, melt, and fill, we'll also have greater life of our granular media. The next thing that I want to address is issues around the chemically bonded sand specimens themselves. The specimens that we look to collect test data for the sake of process control, let's say. We have three different types of specimens in the industry. We have a cookie shape, that is now a standard, the traditional dog bone, and the, I'll keep things in simple shapes here, the Kit Kat bar, the rectangular beam. Well, certainly most people know the dog bone for chemically bonded sand testing. And the shortcoming with this specimen, it does not always break where it's supposed to. Right at the slender, sexy part of the specimen, it breaks across the shoulder to the hip, or across the hip or the shoulder, and so to affording specimen to specimen variability in a mechanical test. On the 3-point rectangular beam specimen, that specimen works well mechanically, but if we try to heat it during test, we can't get any data because the failure mode is premature. But certainly as a mechanical test, the 3-point bend test is excellent for ultimate strength testing, bending moduli, shear, etc. So there are some reasons why we prefer the new alternative standard, the 50mm diameter, 8mm disc. There is no shape factor. If we now go beyond mechanics to look at what is really happening in a metal casting process, thermomechanically, thermochemically, thermophysically, if we take a simple shape like a disc-shaped specimen, we can wet it, we can learn more. The shape is simple, we can build it in our process and not have any residual stress in ejecting it from our tooling. And then the heat transfer factor. Again, the shape factor is simple. If we put heat at the bullseye of our specimen, we know where that heat will go radially and axially. But what is more, in order for us to acquire the proper data, let's call it smart data that will coincide with digital processing in our industry that suffices Foundry 4.0, and more of the reason why we need these highly well-distributed ceramic sands is that the specimens using these materials coming from a process will give us in turn representative and smart data. How we data is what I'm showing you next, utilizing testing techniques on these disc-shaped specimens provided through the AFS. They are new standards circa July 2018. All of these tests are dynamic in nature. What we mean by that, there are multiple properties that we run off of them. For example, in the simple impact for mechanical properties, we could understand the impact properties before the specimen sees elevated temperature and after elevated temperature. so that we could understand the mechanics in shakeout or retain strength. We can look at ambient to hot venting characteristics. So the hot permeability test is telling us, can we really vent when the action is really happening, when we put heat onto that sand system? And then the abrasion test will tell us about cure characteristics, hot to cold. But the preeminent tests around these are two. We can do a fast LOI, a VOC, and moisture in less than 5 minutes. But the preeminent test that gives us time series data, which is also part of smart data for process control, is the thermal distortion test, also known as TDT. So this is a semi-automated test at this stage. The specimen is brought in direct symmetrical contact with a hot surface. While we monitor temperature at the bottom, there's a sensor right there that tracks the temperature gradient from hot to the backside. And then we can look at the specimen in 3D as it expands radially. It's 50 millimeters nominally, and then it's expanding here in real time. We also measure what is happening axially, and as well, as I mentioned, the thermal issues, and we're getting that data 3D in near real time. The specimen comes out of this test typically intact, even though it's free to bend. The specimen is only supported 1 millimeter around its edge. So we have very valuable data, and again, time series data that allows us to do certain types of predictive analytics. And I'm going to explain how we can study those things. So what we do to these new test specimens, we affect how they are blended or potentially the additives that we could place on them externally, like a refractory coating, or internally as other types of chemicals and compounds that we could add to the sand. Here on this slide, I'm showing you at the top left a silica sand system as a disc, and similarly on the bottom left, you're seeing a ceramic sand. To the far right, you're seeing a recipe that is 50-50 in the mix, and a distribution representing such that you can see 80-20, 20-80, 40-60, 60-40, and we can understand how we could blend these systems if in fact there are some potential advantages thermomechanically, thermochemically, thermophysically, etc., etc. The other thing that I wanted to make good mention of in terms of trying to get good qualification strategies from these advanced materials like ceramic sands is in the testing themselves. And we have to do that on these substrates that are discs that we glean from the process itself. We need to get that at line speed, or if you're dealing with a jobbing type of process like 3D printing, we need to get those specimens as we build them in the box at different depths, at different ricotta angles. Because what we're asking is, does these sand dish-shaped specimens or these ceramic composites, are they varying mold to mold, core to core? We also need to know whether or not these dish-shaped specimens vary castings to castings. And we'll show you how we get at that. This is very important because when we have a superior engineered material, we want to make sure the warranty and guarantee complaints that we may be getting on the foundry end is not due to the ceramic. So we have developed some casting trials as part of this qualification mode. This one happens to be an erosion model. To show you how this works, it's several specimens that we can wet simultaneously from a given chemistry, at a given head pressure, at a given temperature. And I want to let you know that everybody in the foundry industry loves to look at temperature. They see the excitement, the danger of temperature, but we want to let you know that head pressure is equally as important in preventing mold metal interfacial defects. But why this is important? These types of testing can allow us to respond to the higher order engineering tools that we have available, like solidification simulation. When we understand the velocities and flow that could cause us deleterious circumstances in our casting process, we could get that digital data, whether it's a photograph, a picture, or actual boundary conditions that we could upload into our solidification simulation software. And we'll show you how that works in an upcoming slide. On this next model, we call it the cookie and donut model because there are cookies that are shown in the drag half on the mold to the right, and we place that in symmetrical order on a core print where we wet these specimens again from a given head height at angles and through a filter that will allow quiescence. Recipes, different head pressures, etc., to understand what would cause certain concerns. And here are some of the classic concerns: the veins, the penetrations. These particular terminology are foundry defect terms. You're not going to find them very well if you Google them. The point is, we want to prevent this and as well as get a superior surface roughness relative to the as-cast surface. That is important. We can evidence this today non-contact. With technologies like I'm showing you here, a 3D macroscope could show us what is happening on our dish-shaped specimens in the molding room. And then in the finished room, we can see this on the casting. We can get surface roughness, volumetric change, ambient temperature differentials. We can have that data. So any shift between the molding room to the finishing room, we know that digital data, that digital shift, we could be responsive to and give information back to the foundry in near real time. So regardless of the process, we need to qualify the sand binder systems for the head pressure, temperatures, and chemistry. Again, the AFS work that is documented and available through them is devoid of a proper understanding on steel castings. We have started that work where we are understanding the mold metal interface at steel head pressures and temperatures relative to surface conditions like shakeout, and then the surface roughness to come up with an overall measure for casting quality. On this slide, I'm showing you a system that could shake out well at a core print for the same energy, and another system that can't shake out on a steel casting, even with a ceramic sand. And this is because we did not understand the combination and the fluxing concerns that may happen if we inappropriately choose a wrong engineered scenario for these sand binder systems. So that needs to be studied, and we are ready to do that. So these are the ideas behind our thoughts. So a statement that was made on our AFS research is my closing comment. There is no panacea for alternative granular media for use in our foundry industry. We must qualify them and understand the thermomechanical, thermochemical, thermophysical considerations to make superior castings with superior materials, such as the ceramic sands. Thanks for your attention.
Thank you very much, Dr. Sam. This is very informative. At this time, we're going to switch over to Jerry Teal and let him talk some about what he's doing at UNI.
Well, good afternoon. You should see my screen now.
Yes, we do.
UNI has been working with ceramic molding media for over 20 years now. And that gives us an advantage of seeing it develop from a industrial proppant for the oil and gas industry into an engineered molding aggregate for demanding applications in the industry. Most of the information you're going to see presented by me today was a result of an AFS research project, which was requested, and the evaluation of alternate materials to replace silica sands in green sand molding systems. So most of the information I'm going to present is angled towards or targeted towards replacing silica, but in a closed loop system where new material isn't added continually for green sand dilution. We worked with 3 materials. Our base material, or the was silica sand to be compared to. The ceramic A was a agglomerated domestic grade product produced in the US. Ceramic B was a Chinese imported material. And we'll see some differences later on in those materials. When do foundries use alternate materials? Of course, we know that silica sand is the most abundant and most cost-effective molding aggregate in the industry, although it comes with issues. People use ceramic materials aggregates when the performance limitations of the silica sand have been exceeded, or their environmental controls are inadequate to meet the regulations. And those regulations I'm speaking of would be the OSHA permissible exposure limit for respirable silica in the foundry. Baseline information for the 2 ceramics we tested, they were both around 55 GFN. We chose that because that probably is a very common GFN for both iron and steel foundries. Similar pHs, similar ADVs, both very low. Similar specific surface areas, both very round in their shape, with similar densities. One of the first tests that we perform on materials for looking at the applicability in molding processes is some high temperature thermal expansion testing. We want to make sure that, one, we're not seeing drastic changes in the morphology of the material or thermal breakdown due to high temperatures. We'll run our tests up to 1650 degrees C, which is much higher than normal pouring temperatures for iron castings. And as we increase the temperature, we put a small amount of force on that sample. And what that allows us to do is see very accurately where the center point of those materials are. To define the center point, it's the point which we get liquid on the surface of the sand or the bead that allows those beads to adhere to each other. So if we've seen silica sand castings, heavy gray iron, we usually see a small adhering layer of sand that's easily broken up. That sand is exceeded the center point, so it adheres to itself. Looking at the green sand thermal expansion, and these were all bentonite bonded samples, we can see the ceramic A has a minimal amount of expansion. Silica sand will have around 0.14 inches per inch. These aggregates had less than 0.004 inches per inch expansion, peak expansion. We see the ceramic material coming back to 0 or losing some dimension around 2400 degrees C. Ceramic B, slightly under 2400 degrees. When we look at the center points of these 2 materials, we can see that the domestic product, ceramic A, had around over 120 degrees higher center point after 5 cycles. Now the cycles include mixing the sand, mulling the sand with bentonite, producing castings, shaking those castings out, and having a proportion wet reclaimed back to new. We did this because then we proceeded to make cores, phenolic urethane cobalt cores, out of that reclaimed sand, and then use the balance of the reclaimed sand plus the cores for our green sand dilution. This was a closed loop system So every bit of sand that was used in cycle 1 was also used in cycle 5. So this simulates a foundry being able to use that sand over and over again. We can see a decrease from cycle 1 over to cycle 5 because we are building up some contamination on that sand that was not reclaimed. We feel that in previous research has showed us between cycle 5 and cycle 8, we reach equilibrium, where we no longer see a decrease in the center point of the sand. It also should be noted, this is the same for silica sand or any of the molding aggregates you may be using. Our attrition testing was based on what has been done historically in the Sand and Gravel Institute. The American Foundry Society does not have a breakdown or attrition test. We had to borrow someone else's. We did this by placing 5 pounds of the aggregate along with 5 pounds of ceramic tumbling media. After 4 hours, we would separate the tumbling media, and then test the sand in screen distribution. One of the important points I want to bring up, it was brought up before that there would be performance advantages in using blends of ceramic and silica. And that oftentimes is true. Casting quality, casting surface can be improved. The issue with doing that is that the ceramic material has almost twice the more hardness as some silica sands do. So you can imagine using both of the materials in a system, a green sand system. The ceramic material will actually grind the silica into dust. So if the ultimate goal is reduction of respirable silica dust, this does not help. It actually increases the dust generation in a foundry. Now the AFS index, or the attrition index we use, was something very simple. It was the original AFS GFN, the difference between the original AFS GFN and the AFS GFN after the material went through the attrition test. There's something really interesting you should see on this. The blue is the original. The blue line is the original before attrition value or screen distribution of that sand. The interesting point is the balance of the curves, the results, are attritions 2 through 5. Notice that the majority of the breakdown of the silica sand happened after the first or during the first attrition. After that second cycle to the 5th cycle, there was very little change in attrition index or change in grain fineness. We can compare the ceramic A attrition with the ceramic B, and you can see the changes. Ceramic A lost quite a bit less, resulted in quite a bit less on the 270 in pan. The 270 in pan screens are representative of the silica dust that can be generated with that sand. It is not respirable at that sizing, but it is representative of the amount of dust. We can see on ceramic B, we had quite a bit more on that 200, 270 in pan. So that material was breaking down to a finer extent than the ceramic A. If we take a look at it in tabular form, we can see that the attrition index in the silica was 28 grain fineness numbers. In ceramic A, less than 6. and ceramic B a little more than 11.5. So major improvements in the breakdown of those sands. How do we measure the respirable dust? Well, we looked at measuring real-time results. So anytime we move sand, whether it's off the end of a conveyor belt, whether it's off the end of a continuous mixer, we see dust being generated. We want to be able to measure that dust when we move the sand. So we are looking in the range of respirable particles measured in micrograms per cubic meter in the range of 0.1 micrometer to 10 micrometer range. So this device was able to measure up to 20,000 micrograms per meter cube, much over the OSHA standard PEL. The general layout, we have a funnel. We drop the sand through a 1/4-inch diameter hole, falling approximately 40 inches. Now this is done dry, unbonded. And then the sample of dust was collected from the dust monitor, measured as peak as well as time dependent. So we could measure both the amount of dust coming off and also the peak amount that would be measured in the device. So what we're seeing is, we could take a look at, this is a new Illinois high silica round 60 GFN sand. The sand hasn't been used in an operation. It is strictly a representative sample off a load of sand. We can see peak respirable silicas in the microgram per meter cubed of over 650. While the ceramic A, which was tested twice, was under 25 micrograms per meter cubed. A dramatic difference. We also, because this was a test for green sand applicability, we did what was called a mull down test. Now what we do in this is we mull bentonite sea coal in water with sands. And then we measure the initial properties after 5 minutes of mulling in a 2-wheel or vertical wheel muller. And then we measure the properties every minute out to 12 minutes. What we're looking for here is the bond development. We know the longer we mull sand, the higher the properties will be. But that rate of increase in properties gives us a measure of how well that material is going to develop strengths. We can see that both the ceramic samples mulled in with higher values faster than the conventional 55 GFN silica sand did. If we take a look at what we call the muller efficiency, and that is how well we are developing those properties, and you can see the calculations on the bottom of the screen. Once again, we see that the ceramic material had a higher mullering efficiency than the silica material did. This is an advantage. This means more consistent, higher properties with an engineered material. Is there any questions? Well, we can go on to the question.
Thank you, Jerry. Thank you both, Dr. Sam and Jerry Teal, for your presentations. Those were very informative. And thank you, the audience, for your attention. At CARBO, we strive to provide technical support for all our products, including metal casting media. Now for a few questions. Let's see what we got here. This one's to Dr. Sam. Why was the ball mill test created?
Okay, the question reads, why was the ball mill test created? Well, what happens in terms of foundry media is a number of thermomechanical types of issues. But if we looked at things from a mechanical perspective, certainly impact is there through the process, through mixing and blending, all the way through finishing, and especially in shakeout. And so the idea of impact is tantamount to the understanding of breakdown. And that's what showed up to be a critical issue in terms of depreciation of granular media. However, again, I want to reiterate, there are some granular media that are superior in resistance to this particular action as well. Thanks for the question.
Okay. Next one is for Jerry. Is centering temperature the point at which the material fails?
The centering temperature is the point at which we develop some softening of the surface of the aggregate and we get adhesion without any binder. So that would be the point when the sand starts to stick together rather than a failure.
Okay, next question is for both of you, and that is, which material was the CARBO in the data you presented today?
In my presentation, that material was pointed out as material A.
It was also material A in my presentation.
Okay. Last question that we have time for today. We have heard a lot about CARBO's new HT material. Have you ran any tests with that material yet? Dr. Sam?
I'll go first then. Yes, I have. Recently, we've had some casting trials with steel, and we've done some laboratory tests on cookies with one sand binder system, resin-coated sand systems. And this particular work is really being refereed currently for publication. So what I could say is certainly in terms of the HT material, comparing it to what we use in this study at iron temperatures, it outperforms the AccuCast materials in terms of elevated temperature stability, and then wettability. It's superior there in shakeout and as cast surface finish for steel.
Yeah, we see the same thing with higher refractory values, higher center points, greater mechanical strength when bonded with chemical resins, and also superior surface finishes.
Okay, well, thank you both for your time. And I want to thank everybody else for taking the time to watch the webinar and submit questions. That's unfortunately all the time we have, and the webinar is recorded, as I mentioned before, and will be played back, can be played back at your convenience. We'll have it up on the website hopefully tomorrow. Additional information about metal casting as well as other CARBO technologies available on our website as well. Please feel free to contact us directly and ask any questions you have. Thanks again and goodbye.